Ben Cohn. Hope you're doing well today. It is beautiful outside, though it is a little bit dreary. So we're going to wrap up the physics course, the AP Physics, studying for the AP Physics exam. We're talking a little bit about AC current. So specifically, we're going to talk about LRC circuits and then motors and generators. So this won't be on the test, but you basically know everything to already understand these concepts, but it's never presented to you. So the reason I like to go over these concepts is I think it helps solidify some of the knowledge you already have. When you see this, information you've already been given, and you see it applied, then I think it helps you understand what's going on a little bit better. And even though you won't see a lot of these concepts by name, they might introduce them to you kind of in a problem setting. So it's good to know these things. Don't stress out because you won't know the details, because I'm not going to present. This is going to be kind of a very 10,000 feet view type thing. So without further ado, LRC circuits. So LRC stands for L is for inductance, R is for resistance, like you know, and then C is for capacitance. So I'm going to start with capacitors. So the capacitor is basically just two plates. So we have a battery, probably throw in a resistor, that way we just don't have infinite amount of current. A battery and two plates. And so what happens is we have negative charges. So we have a current that goes this way, and we have negative charges that go this way. The negative charges pile up here. They repel the negative charges over here and forces the negative charges to continue their flow through the system. The way we approached this from a hydraulic analogy was we said that it's kind of like a diaphragm, where we have current going this way, and we have a piece of rubber stretched across the pipe, and then the piece of rubber stretches. Initially, the piece of rubber will push the water on the other side, and it'll continue the flow through. This is why we said when we were talking about capacitors that initially capacitors act like a short, like a straight piece of wire, but in the long term they act like an open circuit. So to draw that out, we have battery, resistor, capacitor, and then back to the battery. So right here, that piece of wire at t equals 0, that's basically the capacitor. That's the way the capacitor is acting, as if it wasn't even there. And then for a long period of time, it's going to act something like this. Also like the capacitor isn't even there, but this time instead of being a straight wire, it's going to be approximated as an open, so no more flow. So if you look at it as current with respect to time, you'll get something that looks kind of like this. So you have, I'm going to call it Imax, and Imax will be found by the voltage and your resistance, where you have I equals V over R, Ohm's law, and then you have an exponential decay until you get down to almost 0. And this will be something along the lines of I max I of t equals I max times e to the negative lambda t, where lambda is a constant. In this case, we use a constant called decay constant, time decay constant, time constant. I don't know, I should look it up. Either way, it's RC, resistance times capacitance. And that is the analogy for a capacitor. Now, I'm going to delete, lock the board in place. There we go. Clean up the board. So now we get something. Let's look at this a little bit differently. So we're still going to have the circuit diagram with a capacitor, and we'll still have the hydraulic analogy right here. I think I'll use green for the diaphragm, and I'll show how it stretches. Nope, too much. Not dotty enough. There we go. And we have water or current going this way. Current going up there. And so this time we've only looked at it with direct current. But now we're going to look at it with AC current. So the idea is, let's say we have time going this way. Let's make this longer. Give us a bigger time horizon. There we go. Whoop. And I'll do a negative and positive. So let's say what we're doing this time is we're flipping the battery back and forth. So it'd be kind of like, we're doing this. 1, 2, 1, 2. And so what's happening is creating the flow back and forth. Now, I know that AC current, the way it normally works, is it goes up and down, kind of like a sine curve. This is going to be more of a step curve. I guess step function is probably the correct way of saying it. So we'd have something like this. So we get starts at high, comes down, like this. But then when we switch the battery around, it'll immediately jump down. And this will provide us a negative current. By negative, I just mean the opposite direction. When we really don't care about negative or positive, we care more about the magnitude, the absolute value. And the reason for that is there's a component called a diode. The diode allows current in one direction. Long story short, we can arrange the diode in such a way that we can basically flip current so that we only get the magnitudes. Full bridge wave rectifier. Probably said that incorrectly. But that's the idea. Diodes. So the magnitude is what's important. And so you can see here, if we flip it at just the right time when the current starts to die off, then it flips back and forth. So now the question would be, so you're like, all right, so what kind of defines long time here? Because, okay, it seems like it's flipping at just the right time, but what if instead we waited a long time and then flipped it? What would this look like? Well, and so it could look something kind of like this. So it comes down and it's basically flat lines. Then you flip it, it comes like this, and comes like this. And so when you look at the power generated here, power equals IV, and the current here is, or I squared R, or V squared over R. The current only exists for a very small time between when you flip it and unflip it. And so what happens then is we're not generating a lot of power here. For the most part, this thing is almost always off. It's on for brief periods, but it's almost always off. And so if we have a very slow switching, then it produces very little power. Another way of saying that, if it's very slow switching, it'd be to say that the frequency of an AC circuit, the frequency is low. Another way to look at this is, if we have a very low frequency with a capacitor, it's going to provide a very large resistance to flow. Which brings us to another concept called electrical impedance. So electrical impedance can be defined as in opposition to electrical flow. Now your thought process is, all right, we already learned this. It's called resistance. We have resistance in opposition to flow. Why do we need this other electrical impedance thing? So I'm going to say Z equals I over V, which before we always said that R equals I over V. And this will be electrical impedance. Well, the difference with electrical impedance is it includes things that really don't have current flowing across it. So if you look at our capacitor, this is a fairly reasonable representation of capacitor because you have two metal plates with a gap between them. And if you don't have a dielectric, you can have an air gap capacitor. It's a real live capacitor. and you don't actually have electrons flowing across it. So if you tried to measure the resistance of a capacitor, it's like, well, no electrons flow across it. It's the electric field that's generated between the two plates that allows current to flow. And so if you don't have any electrons actually jumping this gap, you sometimes do. That's mostly called arcing or dielectric breakdown, or lightning, if you will. And so, but traditionally you don't have electrons jumping. So if you don't have electrons jumping, then you really can't define it in terms of a resistance the way we have been with resistors. Which is why electrical impedance is a useful measure. Well, one other thing is the electrical impedance depends on the frequency. As we discussed here, a low frequency for a capacitor will create a very large resistance to flow. And so we need a way of capturing this resistance to flow based on the frequency of the alternating current we have. Now I say alternating current, and I mean both the sine wave type or just little step diagrams where we have, looks like a castle parapet, where we have just the square block diagrams. Either this or wavy style. Either way, when you have quick changes of frequency, that's what I mean by frequency. So the way this is modeled is using imaginary numbers. So let's say here, this will be real, this will be imaginary, and so resistance is measured on the real axis, real resistance. Impedance for a capacitor, I'm going to do Z, C, Z for impedance, C for capacitance, is modeled as 1 over J omega C. So J here, it's the same as I for your imaginary number. So J is the imaginary number. You square J, then you get -1. Omega is angular frequency. So omega equals 2 pi f. It's just more convenient to throw that 2 pi in there. So we use omega. And then C is capacitance, measured in farads. And so when we measure this, we measure it as a, and on the imaginary plane, imaginary axis. And one thing you can think about with this equation, get rid of some of these, we take this equation and we multiply it by J over J, which is just 1. If you have the numerator and the denominator are the same, it's the same as multiplying by 1. And you can always multiply by 1 in life, mostly. You get J over J squared omega C. This J squared becomes -1, and you get J over omega C negative. And so right here we'll have omega C as this vector. And so the impedance, this will be the imaginary part of the number, this will be the real part of the number, and the total impedance that we have will actually be this hypotenuse right here. So it'll be R squared omega C squared, and then R squared plus omega squared square rooted will be the hypotenuse. And that'll be the impedance that you see for the for your circuit. So let's look back at this circuit real quick. So we got a resistor, we have a capacitance, and now let's say this is still a direct current. So if we saw here then with our capacitor, then we would do the real times the imaginary. I think I did this one wrong. Outrageous. Purple. 1 over omega C. And then we squared it, square rooted. 1 over omega C squared. Okay, 1 over. So the impedance for this system, the resistance to flow, would be 1, let's see here, we do r squared plus 1 over omega c squared square rooted. And this would be the impedance, which would equal the current divided by the voltage. Therefore, the current, if it's direct current, then the omega, the frequency is 0. It's not oscillating up and down, it's steady. And so what you would get now, immediately when you flip the switch, you have to wait a little while for it to even out, to equilibrate, so to speak. But you get this omega right here, that goes to 0. You do 1 divided by 0, with the exception of the universe exploding. What happens then is your impedance goes way up. I'm going to write this more as I equals impedance, which is that, over R. I can redo this better. So I equals V over R, which equals whatever our DC voltage is, R squared plus 1 over omega C squared square rooted. There we go. That's better. So what happens then is this goes to 0, which means that 1 over 0 goes to infinity. Square root of infinity is still infinity, which means that the denominator goes way up, which means that the current will go way down. And so what happens then is this is how we can model capacitors using a frequency and imaginary numbers. I know, a lot of information real quick. Don't expect you to understand it. But when this comes across at some point other in life, you won't panic. Because you'll be like, oh, okay, I kind of saw what was going on here. We can model the capacitor as having something that's similar to resistance, which we'll call capacitance, or impedance, which is 1 over imaginary number j times the angular frequency times c. And that will tell us that based on the frequency, how much resistance to flow we're going to have. Cleaning up the board real quick. If we take example from the other direction, where we have a super high frequency going back and forth, and if you think about it from the hydraulic analogy, you have your pipe, and if it's going back really forth, then the diaphragm never has a chance to stretch very far, so it's providing very little resistance because it keeps stretching one way, then it stretches the other. Looking at it from the instead of looking at it from a current and time point of view with a very high frequency, instead of the current dropping like this, it just starts to drop just a little bit in blue. Ooh, cyan. So you'll have a little bit of drop, and then it'll automatically switch down to the other side. Little bit of drop, little bit of drop. And what happens is you're not really losing a lot of the energy. And so if you have a very high frequency, the way that impedance would be modeled would be similar to before. Current would equal voltage over, and then it would be R squared plus 1 over omega C squared quantity square rooted. Well, if the frequency is really high, then this denominator goes really high up towards infinity. 1 over infinity is 0, and you're left with basically V over R squared, which is V over R. So a very high frequency is as if that capacitor wasn't even there. It's modeled as a short, which is kind of intuitive to what we were thinking before. That's the idea with capacitors. Now inductors, which are basically just coils of wire, solenoids if you will, kind of fall under the same idea. So if we draw this up, we have a battery, we have a resistor, say a resistor R, and some sort of inductor. Oh, just like so. That's pretty good. And I'll have an inductance of L. Now the hydraulic analogy for an inductor, green pipe. Nope, I can do that better. Pipe like so. There we go. Is a water wheel. So what happens in the hydraulic analogy model is you have water go this way. It immediately hits the water wheel. It can't get through because the water wheel has significant momentum. But after a while, the water pushes it and brings the water wheel up to speed. And eventually, the water wheel is just spinning and not really offering any resistance to the current flow. Similar with a conductor, with an inductor. So at t equals 0, we have our battery, we have our resistor, and then our inductor looks like a short, which is opposite from the way the capacitor worked. But at t equals infinity, our inductor will look as if it's a short, so it'll allow current to flow straight through with no resistance to flow. And your thought process at this point is like, okay, I've seen where this is going. You talked about something similar with the capacitor. Is there a similar imaginary way of looking at a inductor, just like there was for a capacitor? Why, yes. Yes, there is. And for an inductor, dark purple, I'm going to say ZL, Z for impedance, L for the inductor, is J omega L. I should draw up the timeline too for an inductor. This will be T, this will be current, very little to start with, and then it asymptotes out. There we go. And then if we're switching, I'll draw this up here real quick. T, I. If you're switching it, you get something that looks kind of like this. Like little sharks in the water, so to speak. Pump. Pen. Where it ramps up to asymptote, but then it switches and then ramps up to the lower level, ramps up to the top, ramps down again, etc. And so this is modeled by J omega L, where again, J is the imaginary. So it's kind of like I, where J squared is -1. Omega equals 2 pi f. And L is inductance measured in henries. IES? I don't know. Or do they keep the Y? Not sure. Mystery of life. So the idea here then is if we have a very slow switching, then what's going to happen then is you get something like, this will be for low frequency. Low F also means a low omega. You get something that's like this, and then eventually it'll switch, ramp up, and then it'll be like this again. And so you'll have lots of current. This will be T for time, this will be I for current. And so you'll have lots of power going through with a low frequency. But if you have a high frequency, this will be T, this will be a high F, this will be current, you get something kind of like this, where it never has time to fully ramp up or ramp down, and it's just kind of stuck in this back and forth where you have this water wheel that's getting jittered back and forth without actually doing any work or allowing any current to really go through it. And so when you look at this on a graph with real and imaginary, what you get is something kind of like this. So you have your graph. Red is just too bold for a graph. Too bold. There we go. Nice, calm, tranquil green. This will be real. This will be imaginary. This will be an arrow. And it'll also be an arrow. Where now j omega L will be up in the, let's grab the blue. Okay. So this would be j omega L. This would be the real resistance. And then do some red for contrast. We'd have negative j over omega c going downward. And the j is mostly just to tell you the direction, imaginary or not imaginary. And so this is how you can model impedance. So the next question is, well, what happens when we have capacitors and inductors together? So if you have an impedance of j omega L, then a high frequency provides resistance to current. But if you have a capacitor, it's negative j over omega c, which is a low frequency provides high resistance. Well, so you have basically two ways of putting these together, series and parallel. So let's start by looking at the, too bold. There we go. So we have our battery, but this time it's not really a battery, it's producing an AC current. And this is more of a convention along the way an AC current is drawn in a circuit. And then we have, let's say, a capacitor and then an inductor. So impedance is a combined equivalent impedance is done the exact same way as normal resistances. So for normal resistors in series, you just add them together. And so if you did this, this would be R for the resistance, for the resistor, say C and L. Let's see, capacitors would be minus, I'll say plus negative J over omega C plus J omega L. And this would be the total impedance. Well, if you look at this from a vector point of view up here, you're like, okay, this inductor and this capacitor can be set up so that these cancel out and all you're left with is the resistance. Because if you look at here, we're looking for the hypotenuse, like this, or like that. But if J omega L and negative J over omega C cancel out exactly, if you add these two vectors together so you get 0, you get your minimum resistance, which would just be the resistor. This is referred to as like a resonant frequency. And so you would get something along the lines of, let's see, so you have negative J, negative J over omega C equals J omega L. J's cancel, there's still a negative there, but I'm going to basically ignore it because it's just showing that they're opposite directions. You get omega squared. Let's see, omega squared equals 1 over LC. Cancel this. And then this equals, omega equals 2 pi F. And so when you see people talk about a resonance frequency, it'll be 1 over 2 pi LC, where L is the inductance and C is the capacitance. And the idea is you're just taking your you're taking the impedance due to the capacitor, you're taking the impedance due to the inductor, and you're choosing them so that they cancel each other out. This is called impedance matching. You'll see musicians talk about this every now and then to get the speakers just right. And so what this is doing is it's saying you have a minimum resistance amount. And so if you have a graph, so to speak, where this is maybe frequency, this is angular frequency, 2 pi f, and current, the amount of current that's being allowed to pass through, then you would get something like this. It wouldn't actually go to 0, but we're going to say it does for now. And you get some point in the middle, we have maximum frequency that's allowed to go through this. So this would be a filter you could use to filter for one specific frequency. And depending on how your filter is set up, it'll be more or less precise. So you would have a predominance of a specific frequency that's passing through, which would be based on your inductor and capacitor. So then the other situation would be, let's see here, erase some of these guys. The other situation we could come up with would be we have the inductor and capacitor in parallel. So we would do that with something like AC source. I shouldn't be drawing so close to the edge of my square. It's okay. I will get over it. Oh, and we'll put in a little resistor here. And you could go through the numbers with impedance being, you add the reciprocals, and that'll be the reciprocal of the impedance. I have faith that you can do that. It's kind of tedious, but it can be done. Long story short, what you get then, instead of having a specific frequency that goes through, you have a specific frequency that is blocked. So if you have current like this, where maximum current is based on your resistor. And the idea here then is you have a specific frequency that has trouble getting through at all. And so if you have just the right frequency, what this does is it prevents a specific frequency from going through the system, as opposed to the series configuration, which allows a specific frequency to pass through. This is filtering out that one frequency. And this is the basic idea for filtering out I guess frequencies. When you hear about electrical filtering, that sort of thing, or cleaning up an electrical signal, this is the kind of thing that they're talking about. When you hear about filters, what they're really saying is we have a certain number of capacitors and inductors, and they kind of even out. Another place where this comes up with is in industrial environments. So in industrial environments, they're always operating at some sort of impedance that's not zero, because they have some capacitors and they have some inductors in the industrial environment. A lot of times you'll hear the phrase power factor, and power factor, when they say that, let's say this industrial environment is operating with more inductors than conductors, which is almost always the case. Then you would have some theta here. That theta would be this angle of this triangle generated with your inductance and your resistors. Well, the power factor just equals cosine theta. And so when you hear power factor, that's what that's referring to. Industrial environments almost always operate with more impedance than, or inductance than capacitance, because industrial environments use a lot of pumps. And pumps are basically a coil of wire that has a motor on it. It's a motor using a coil of wire which causes things to spin. And that coil of wire, though it's not meant to be an inductor, it is an inductor and acts as an inductor. And since industrial environments have a lot of pumps, they have a lot of inductance, and that lot of inductance then will create a positive power factor, i.e. this angle being above the x-axis, greater than 0. But you also see with various rectifications and ways of power generating that they can add capacitors. So industrial environments naturally have a lot of inductance, but you'll see with some of the power generation and switching techniques that some more capacitance will be added in. And one of the benefits of that, not only with saving the money through the power switching and generation, you will save energy and therefore money based on adding the capacitance as well, which is kind of an added benefit. So that is the general idea behind how you can combine capacitors and inductors to create filters, which then gives you impedance. I know, massive amount of information. You're not meant to be an expert at this. This is just so that when you see it again in the future, or when you're reading some sort of technical manual, you can be like, oh, I have a basic idea of that. You already know all this information. It just really isn't presented to you in physics. It's not until you get past the first AP Physics class that you're like, oh, okay, here's some electronic system design. So next time, we're going to go over basic motors, DC motors, AC motors, specifically just synchronous, and we'll talk about transformers as well. So thank you for listening. I appreciate it, and I will see you guys next time. Thanks.